Hi. Did you know that when you gather 4 times as much light, the SNR only increases by 2? So gathering 4 times as much light is only twice as far. What? Giant Dr. Detail. No, Dr. D. I didn't mean to. Ugh, that's wrong. Totally and utterly wrong. I'll explain it to my counterpart, and he'll explain it to you. Welcome to Deep Sky Detail. Ouch. Oh, so hi. I had a talk with Dr. Detail. He's seen a few videos saying that gathering 4 times the amount of light in a given amount of time means the setup is only twice as fast. And it's been more than one video, so we thought we'd try to nip this in the bud. Because this channel has been about SNR and its measurements, this intrigued us. And honestly, I was skeptical of the claim, but does the claim have merit? Let's take a look at it two ways: the narrow definition of speed and the SNR definition of speed. So why would people think that gathering 4 times as much signal only increases the speed by 2 times? Well, when you gather 4 times the signal, you are increasing the noise, usually the shot noise and the light pollution noise, by 2 times. So the signal divided by the noise, or the SNR, is only double. SNR is kind of like a measure of an image's quality, and so you're only kind of doubling the speed of the system according to this argument. It sounds and kind of feels right. Well, I don't think it's true. And let me ask you a question. Without thinking too much, does it really make sense that quadrupling the number of photons you collect only doubles the speed? Admittedly, it is really easy to get confused. I get confused about it all the time, especially when the concepts are really similar. SNR and speed in astrophotography are really similar concepts, just like length and time are similar. For example, in the US, if you ask someone how far it'll take them to drive somewhere, you'll often get an answer in minutes. For example, how long did you have to drive to get there? Oh, it's a short drive. It only takes 20 minutes. The problem with the response is that 20 minutes to drive is not a true answer to how far. A true answer would be given in kilometers or miles or whatever. SNR and speed are so closely related in astrophotography that we often get confused, just like time and distance when driving. And I don't blame anyone for getting confused either. Until I sat down and worked out and tested it, I didn't fully understand it either. And I'll share what I learned. And this idea that quadrupling signal only doubles speed is both incorrect in its narrow definition and in sort of the SNR collecting definition. So let's go over the narrow definition first. What is speed? Speed is how fast something happens. It also implies that things can be relative. With speed, you generally have units associated with it. So 50 meters per second is twice as fast as 25 meters per second. In that sentence, we also have units. We have sort of relativeness. We have time. And keep this in mind, we have all these 3 criteria. The question is then, is SNR a measure of speed? I would argue no. SNR can be thought of as a measure of image quality or detail. Strictly speaking, it's just the ratio of the signal you've collected divided by the noise you've also collected. But we use it in astrophotography as a measure of image quality. Improvements in SNR do not scale linearly with how much you think an image improves. In other words, sometimes doubling SNR will make you think the image is 10 times better. Sometimes doubling SNR isn't noticeable. SNR is complicated. But SNR being complicated isn't the problem. The problem is SNR has no units. It is a unitless measurement. You're essentially dividing brightness by brightness. You don't know how many photons are hitting the sensor per second. There is no measure of time. You can only compare SNR relative to other SNR measurements. It doesn't meet the criteria for a speed definition. What does meet the definition of speed in astrophotography? It has to be something like photons per second, or photoelectrons per second, or ADU per minute hitting the pixels of your camera. We have to have some measure of signal on the top divided by some measure of time on the bottom. And there are kind of 3 well-known ways to quadruple the speed per unit time. The first is to just double the aperture of your telescope. Easier said than done, I know, while keeping the same focal length. This will get you 4 times the amount of photons into the pixels of your camera per unit time. The second is to keep the aperture the same but half the focal length. Same thing, 4 times the amount of signal into the pixel. The third is to double the size of your pixel sides, which would quadruple the area. These 3 things will quadruple the signal per unit time in the pixels. And this is the narrow definition of speed for astrophotography. Photons per unit time hitting your sensor. Going from f4 to f2 quadruples the number of photons hitting your sensor. It quadruples your speed. But what is the sort of SNR definition, or the SNR getting collected definition of speed? And I can hear some of you typing this, but quadrupling signal only doubles SNR, so you're only doubling the quality of your image. Plus, you're only doubling the rate at which you collect SNR. Okay, there are 2 sentences there. The latter statement about doubling the rate at which you collect SNR is just straight up incorrect. We'll get to that in a second, but basically you're underestimating the power of signal. But let's take the first statement. Doubling SNR doubles the quality of your image. Sometimes this can be true, but sometimes doubling SNR has no noticeable effect on your image. Sometimes doubling has a profound effect on your image. SNR can be a measure of perceived quality, but it's a very complicated measure of quality. I don't think SNR is a valid measure of speed in this case, because it's not a valid measure of sort of linear quality. You can't say 25 SNR is twice as good as 12.5 SNR, for example. But let's get back to the idea that quadrupling signal only doubles the rate at which you collect SNR. This is not true. In fact, quadrupling signal quadruples the rate at which you collect SNR. When collecting photons, SNR does not increase linearly, it increases with the square root of the signal. So let's go into my SNR calculator app. Let's do a simple example. So here's my SNR calculator app. What I'm going to do is zero out all these numbers. We're going to pretend there's no sky glow background, there's no light pollution, there's no dark signal, there's no bias signal, and we have an f4 scope and an f2 scope. The camera gain electrons per EDU is 1, camera's read noise is 0, so we have a perfect camera. Let's say we want to have our desired SNR of 100, and we have in our f4 scope 100 photons hitting the sensor every 100 seconds. So we have a 100-second sub-exposure. Let's also pretend that at the same time we're imaging with this f4 scope, we're also imaging with another perfect camera with a scope that has the same focal length but double the aperture. The focal ratio for that setup is now f2. We should be getting 4 times the amount of signal. So we should be getting 400 photons measured on average for every subframe. Now let's take a look at the results. On one subframe for the f4 scope, we get 10 SNR. Nice. For the faster f2 scope, the SNR is 20, perfectly in line with the theory. But how long does it take to get 100 SNR? Well, for the faster scope, it takes about 0.7 hours. Now, what is 0.7 times 4? It's 2.8. Look at this. Look at these results. Pretty spot on. Considering we're dealing with discrete numbers of subframes and not continuous exposure, the f4 scope really does take 4 times as long to get the same SNR. But here's another way to think about it. The f2 scope takes 100 seconds to get an SNR of 20. How many 100-second subs does it take the f4 scope to get an SNR of 20? Let's check. So here's the f4 scope. 1 sub is 10, 2 is 14, 3 is 17, 4 is 20. It's 4. Interesting. So who would have thought that quadrupling the signal you get per second means you get the same SNR in 25% of the time? Interesting. So it occurred to me as I was editing this video that it would be helpful to actually convert SNR into an actual speed, maybe by doing the average speed. So if I'm driving from point A to point B, I'm not always driving at a constant speed, but you can find your average speed. So if it takes me 1 hour to drive 30 miles, I'm going 30 miles per hour, even though during that 30 miles, sometimes I might be going only 10 miles per hour, sometimes I might be going 50 miles per hour. And do the same thing with SNR. So we can think of the SNR as the distance we're traveled, 100, 200, 300, 400, 500, 600 SNR. We can look at how many hours it takes the F2 configuration in the last example to get to 100 SNR, and the F4 configuration in the last example to get to 100 SNR. We can then repeat that for 200 all the way up to 600 SNR, and then we can find the average speed, or the SNR per hour, for both the F2 scope and the F4 scope. And then we can determine how much faster is the F2 scope than the F4 scope. As you can see, the speed clearly slows down for both scopes, but for each interval, the F2 scope is getting 4 times the SNR per hour than the F4 scope. If you like... My counterpart obviously didn't understand everything I told him. It looks like we're going to have to do a follow-up video, because there's more to this story. If this video, consider subscribing and watching these other videos I did on SNR. Thanks for watching.